through the whole thread of thought that went on in this long lasting project. Okay. So I'll start with something very basic, and so I start with a brief overview of what differential Galois theory is. So everybody studies Galois theory in the basic university education, but differential Galois is less well known. So I thought it useful to run quickly about this. So the most basic setting is that you give yourself some rational matrix over complex numbers. So this is the classical setting, and you set out to study these differential systems. Okay. So the success of Galois theory, right, made people think, well, maybe we should think about studying also Galois theory for solutions of differential equations. So instead of just algebraic equations, and this was the idea that was in the air already by Lie himself. Okay, and it was taken up by Picard and constructed these Galois theory for the solutions of E. Okay, so what is the main point? The point is that you would join all solutions. Okay, so you consider this ring R, and you put all solutions inside of it, right? So this means that you put formally coefficients, right? Y, AJ, just like you do in standard Galois theory, and you force the differential operator, the derivation, to be extended to R by this formal rule. Okay, so each column of the matrix, which is here, becomes a solution of the differential equation. Okay, but the problem here, so there's a small technical problem, and is that this ring might not be a field. Okay, and what happens is that you might have some ideal inside of this ring, which is invariant to ddx, and this causes trouble. And well, but the solution is somewhat simple. You define the splitting field, right, which in this context is called the Picard-Vestiaud extension. And what you do, you just take the ring and you kill some maximal ddx invariant ideal, and take the quotient and take the fraction quotient, okay? And this happens to be a field. So this guy here is a domain, and this is your splitting field. So that now it's you just follow the same path as in Galois theory. You call the Galois group the group of automorphisms of the splitting field, which in addition preserve the derivation. Okay, so that's the basic idea behind that. And so this, as in Galois theory, the nature of the group Gal should give you some information about how you solve this differential equation. Maybe the most famous result is Liouville's theorem, which says that if this guy here is, if this Gal here is solvable, then you can solve your equation by exponentiation, logarithms, and integrations. Okay, so this is the early steps of this theory, and now the question attached to that is what kind of group is Gal, right? Because it doesn't look like a finite group. It shouldn't be a finite group, and then for that you will need Lie groups or linear algebraic groups at least. And how do you see this necessity of linear algebraic groups? What you do is that you see that your matrix Y, the one which was introduced before, it gives you a solution to this system. Okay, so it's a formal solution. It was constructed for this reason, and it's moreover invertible because it was also constructed for this reason. So basically, it gives you all possible solutions. And since it gives you all possible solutions, what happens when you apply it to apply one of the automorphisms of the Galois group, so you get a new solution because sigma will preserve derivation and everything. So what happens is that the new solution will be just a multiple of this fundamental matrix Y, right? And because of that, you can see every element of your Galois group as a matrix, an invertible matrix. So you get this map, C goes to C sigma, and you obtain that your Galois group is a subgroup of GLNC, okay, which is just like in Galois theory at the beginning, you would throw in the Galois group inside a permutation group, and you say that, well, you have a group which is a finite group, so it sits inside some permutation group. So here the moral is that you have some linear algebraic group, so obviously it sits inside some linear algebraic GLN. And well, if you work a little bit more, you see that this group Gal is closed. So it's really a Lie group or a linear algebraic group. Okay, so Zariski closed. Okay, so this is a very basic differential Galois theory. Okay, so this is what, more or less 100 years now, and then of course the main ideas are Picard and Vissieux, and then came Cauchin to give some substance to the theory of linear algebraic groups and give some solid foundation to this theory. But the way I see it, at least for the purpose of this talk, you can reinterpret this theory. You can connect it to two different approaches. Okay, and these are the following. The first one is the one that everyone studied in a complex analysis course, which is analytic continuation, right? So you have a differential equation, and you continue it analytically, and you see what happens when you continue it analytically along a path. So I call it the monodromy approach, M. Okay, so it's the approach through fundamental groups and monodromy representations. So this is even older, right? So this goes back to Riemann, of course. Well, and then you have a more modern one which is congruent with the rise of category theory. So when people start studying after the 50s, MacLean and Eilenberg, they started pushing category theory, and of course it was hugely proposed by Grothendieck and his schools. And so you have the other approach, which is Tannakian categories. Okay, so what is the first monodromy approach? So this is also very very simple. So you take an X naught, which is not a pole of A. Okay, so remember A is a matrix with rational functions as coefficients, or formal functions. So the case of formal Laurent series I will not touch now. I will concentrate on this one. So you take a point, and so since it's not a pole of the differential equation, you can find a fundamental matrix of solutions. So you solve completely the matrix by your favorite existence theorem in linear differential equations, and you do analytic continuation. Okay, so when you continue, you take a loop about X and you prolong the solution. So you get your analytic continuation along this path gamma. And since Y naught is a fundamental matrix, it's just saying that any other matrix will be related to Y naught by a multiplication by a constant matrix, just like it is written here. And of course, the group that you will obtain, the monodromy group, is the group of these transformations of these C gamma. Okay, so monodromy means that here you can quotient out, so you don't need a pi. You kill homotopic paths, And the reason that this is monodrom is the same way group, right? Is because this C gamma here will depend uniquely on the homotopy class of this guy here, of course. So you get this monodromy group. And the most obvious question you can pose about it is, well, you had two groups, and now what's the relation between them? One obvious difference between them is that the monodromy group is a discrete group, right? There is no reason for this group to be closed, Zariski closed, and the other guy, Galois, is of course Zariski closed. And well, you want to know what the most obvious answer would be, well, if you wanted them to be equal, they cannot usually be equal, but say that you want to be the Zariski closure of the other, right? So, you could ask for that, but that is also, of course, not true as well, as the most obvious example shows. So you take the exponential, right? So the exponential has no monodromy, so it has no singularities. But the Galois group is GM because you cannot find algebraic solutions, and the monodromy is trivial. So this is just a problem between analysis and algebra. So in Galois theory, you're doing algebra; in the other one, you're doing analysis, and the two conflict. But people knew already that the problem, this thing that I said, that the difficulty is between analytic and algebraic properties, came from the inability to solve things by Laurent, by meromorphic functions locally. So this, of course, goes back to Fuchs and Riemann as well on his most influential paper on the hypergeometric functions. Okay, so so what do you do about that? You try to imitate what Riemann and Fuchs discovered. You force the existence of, you ask the question if you can find meromorphic solutions to your differential equations always near singular points. And this is the theory of regular singularities. So I shall say, for the sake of discussion in this talk, that the system has regular singularities is if every time I take a pole, and of course, a pole here is in the Riemann sphere, okay, even at infinity. Every time I take a pole, I can say that I transform the equation. So, I mean, I change variables, okay? And with this change of variables, I would like to have an expression like that. So it means that your new differential equation after this change of variables is just of this form with a pole of order 1. So here I'm using really Fuchs's theorem as a definition. Okay, Fuchs he started with the idea that your solutions must be meromorphic. Okay, and then he worked, and then he came to a conclusion which looks like something like this. So the only equations that have this property will have meromorphic solutions. Okay, so here this is standard nowadays. It's just the definition you give, but it's really a theorem of Fuchs. And well, it was observed by this guy, this Schlesinger, was a German who wrote a very influential book, beginning of the last century, that if you have regular singularities, then you can save what you wanted to happen. And this is this theorem, says that if I only have regular singular points, then the Galois group is just a closure of the monodromy group. Okay, so that's what we wanted. We wanted Gal and Mon to be closely related. And if you have regular singularities, then you are done. Okay, and of course, if you take the time to do the example, you see that the exponential function, which I defined, which everybody knows, when you go to infinity, it acquires a singularity which is not regular singular, because the solution will be the exponential to the 1 over x, you know. So 1 over x is far from being meromorphic. So this is the reason that problem appears. So okay, that finishes the very simple part of this talk, and I'll try to move on to something more categorical, and it's Tanakan categories. So I give myself a field. Okay, so I wanna introduce, I wanna talk about these categories and how to bring them into the problem I'm studying. And so I give myself a field, and I give myself a linear abelian category. Okay, so this category is supposed to have a tensor product. Okay, which is bilinear, k bilinear, etc. And this category is supposed to be living inside of the category of finite dimensional vector spaces. So here k vect is finite dimensional vector spaces, and I have this omega which throws in t inside this vector spaces, and but of course I want this tensor product to be preserved. I want this to be exact, etc., etc. So well, I'll leave many details aside, and the moral is that you have this theorem by Saavedra that says that if you have some other hypothesis, the ideal result is that this category T will be equivalent to the category of representations of an affine group scheme. So pi is some affine group scheme, so you can think of it as a pro-algebraic group. Okay, so a limit of linear algebraic groups. And you have this equivalence. So omega gives you an equivalence between the two categories, T and representations of pi. Okay, so here representation is taken in the sense of finite dimensional representation of this group scheme. Okay, so with this, we go on and define with this machinery once installed on your minds. You can go on and start defining these Galois-Tanaka groups or Galois groups or monodromy groups. This thing has many names in the literature, in the recent literature, and so you define this as such. You define a category inside of your T. So you have an object in T, and you consider the category generated by E and all possible tensor products and quotients and subquotients, etc., etc. And what happens is that you get this category, so of things which are dominated by tensor products of your E, and it's dual. Okay, so here there's the dual coming up, which is part of these, leaving some other hypothesis aside. So I need a dual, but since I left that outside here, I'll leave them as well here. Okay, so once I've done that, I can apply the theorem and I obtain this equivalence, because this category generated by E still satisfies the properties we were looking for before. And I obtain this pi E, okay, which is my candidate to a Galois group. Okay, so this is my Galois Tanaka group of E. Okay, and why is it that I take the time to introduce this? So it's because, like in usual Galois theory, once you have a huge Galois group and you want to splice it by smaller pieces, which is the profinite completion theory. So you want to take finite dimensional extensions and look at the Galois group of the algebraic closure as the limit of these Galois groups of finite extensions, and this is exactly the same idea that I'm pursuing here. And why is that useful? Is that because this pi E, it is a linear algebraic group. So if E, I take E, and now E corresponds to some representation of pi. Okay, so pi is the group of the big category. E is an object in the category T. So by the equivalence, it corresponds to a representation, which I call rho E. And it's just the case that pi e is the image of rho e. Okay, so in particular, this is a linear algebraic group, which is an important feature. So it's just it's not a pro-algebraic group. It's not something very complicated. It's something we can work with. Okay, so are there any questions or remarks at this point? No? Okay, so I go on to the examples. So let me give you the examples of this theory. I take an abstract group, and I take T to be the category of representations of this abstract group. Okay, so this is a category which is k-linear, abelian, has a tensor product, and everything. Sorry, I made a mistake here. I'll go back to full screen. Okay, so it's this abstract group, and I construct this pro-algebraic group, this affine group scheme, which is the algebraic whole of gamma. Okay, but it's algebraic is a bad name because it's not algebraic in the sense of algebraic geometry. It's not a finite type, but usually. But that's the name it is. So you get this affine group scheme associated to gamma. And well, the example I can offer you is over C, the algebraic whole of the integers is just one copy of the affine additive group times a pro-torus. And the pro-torus is really, I mean, it's just a torus with a huge character group given by C star. Okay, so this is the algebraic whole. And the interesting thing about this category is that you have this abstract Schlesinger theorem. Okay, so once you have an object, in this category T, okay, you have T here, and you have an object which is a representation. I can try to compute the Tanaka and Galois group, and I can compute the image of this representation. And well, what happens is that the abstract Galois group is none other. The Tanaka Galois group is just the closure of the image. Okay, so this will play a role in a second when I go to study these geometric parts. Okay, give you geometric examples of T. Very good. So I move on now back to differential equations and geometric theory. So I take a P1 and some points in there. I put infinity in there just to be safe. And I consider the affine space obtained by removing these guys with some ring, so it has some ring of functions. And I introduce the category of connections in there. Okay, so these are the generalizations of differential equations. And the category of connections, I can just define them in the simple way. It's just these C-linear maps which satisfy the Leibniz rule here. Okay. So once I do that, I bring in one point of this variety X with this open subset of the affine line, and I consider the functor which associates to each element in this category of differential equations is fiber over some point. Now, an important feature of these connections is that once I have the structure of the connection on the coherent sheaf, okay, it turns out that the coherent sheaf is a vector bundle. It's locally free. So it allows me to see that this functor at the end is exact. Okay, so in characteristic 0, every time I have a connection, it turns out that the sheaf is locally free. And this makes omega, my taking the fiber at x0, an exact and faithful functor. So this gives me all the ingredients to do Tanaka theory, and I get pi of dE, which is a pro-algebraic group, and I get the Tanaka and Galois group, pi e, which is a linear algebraic group. And of course, as you can expect, so since I said that this was supposed to be a reformulation of the previous theory, I get the proposition saying that the Galois group, which is constructed through Picard-Vessieux extensions and this very Galois style approach, is isomorphic to the Tanaka-Galois group. Okay, so it means that we have recycled the theory in a way that we can only do one. We can only do Tanaka theory, and this takes care of almost everything. Okay, but now the two examples which I ran are the representations of abstract groups and differential equations. Okay, so this is just like before, the representation of abstract given by monodromy, and the differential Galois group given by this Picard-Vessieux theory. So the theme of this talk is just going between one and the other all the time, and how to unite them. So in order to unite them, I introduced a notion. Well, let me do it formally so that you'll not suffer too much. Those who don't know these things will not suffer too much by listening to a talk without definitions. I introduced this sheaf of logarithmic differential forms. Okay, so this is just the differential forms, and I throw in the logarithmic ones, so it's dx over the local parameter near the singular point. Okay, and I introduce the logarithmic connections. Okay, so logarithmic connections are just connections, but instead of having values in holomorphic forms, they have values in logarithmic forms. Okay, so I introduced this category, and I introduced the category of regular singular differential equations, which is those differential equations, as before, which have some model, which can be given a logarithmic model. Okay, so these are the DEs as defined previously, for which there is some logarithmic model which induces it. Okay, so very good. And under this approach, I say that the Tanakian point of view, it ends up containing even the analytic point of view. Okay, so recall that we had the monodromy approach and we had the Tanakian approach, and I say that we can recover, at least so that we can recover Schlesinger's theorem, the monodromy approach by means of Tanakian. And this is based on a theorem of Deligne, which is well, it's one of the readings of his very famous monograph on regular singularities, and says that if you take your differential equation, right, which has regular singularities, you consider the sheaf of solutions, the local horizontal sections, which means that the sections of E which are killed by nabla, okay, this produces you a local system, okay, and doing analytic continuation of the local system, or doing analytic continuation of the fundamental matrices, you will obtain like a representation, which is the monodromy representation. And Deligne says that for regular singularities, this will be an equivalence. Okay, so this is an important theorem. And now we recover Schlesinger's theorem with one blow, which is given like that. So I have the Tanaka differential, Tanaka-Galois group of E inside the category of differential equations. It turns out it's not hard to see, but it takes you a good 10 minutes to realize that. It's not hard to see, but it's not completely obvious either, that if you do you have two categories here, right? You have D regular singular, and then you have the usual D, okay? And you compute this Tanaka-Galois group inside D and inside D regular singular, okay? And it just turns out that they are the same. This is a lemma. And well, once I apply that, and I apply that D regular singular is just representations, okay, then I know that the Galois-Tanaka group, from what I said before, will be just the closure of the monodromy, okay? So it will be just the closure of the representation, as in the case of representations of abstract groups, okay? So this is the first part where I make use of the fiber functor. I make use of the. So any questions at this point? So maybe it's too fast. So let me know if I'm not I'm missing something, and if you're listening well. So let me see. Okay.
Yeah,
so
it's good.
It's fine.
It's continue.
It's good. It's okay. Okay.
Yeah, it's okay.
Good. Okay. So just to see to avoid that. I'll bring your shared window to the front. Okay. So okay, good. So well, let me go on. Sometimes it's difficult to see T. I have a category which I cannot embed in K vector spaces so easily. Okay. So for example, the one I was starting with, I can have these formal differential equations. Okay, so these are just finite dimensional K Laurent vector spaces. Okay, in which you have this this Leibniz rule holding. So mind you, here I put an X here. So this is not the usual Leibniz rule, but it's the Leibniz rule for the derivation x d dx. And this is just a standard in the theory because I want to have a formal regular singular, which means that I look for, oh, so this is a typo here. So yeah, oh no, so this is okay. So this should be formal. And I look for the differential equations which are regular singular, okay? Then that means that I can find a lattice inside of E, which is invariant under nabla. Okay, so nabla invariance is, why is it good? It's because I fixed this derivation here to be x d dx. Okay, so these are the formal regular singular. And if you ask right at the start, if you ask me like that, so okay, this category looks very nice. It has a tensor product. You easily define duals and things like that. But I cannot see how you're going to throw this category all inside of K vector spaces. It's not easy to associate to such an object a K vector space, of course, because of course this is a Kx vector space. Okay, and while this is one of the things that another thing that Deline did is that at least if K is algebraically closed, then you can throw in this formal all inside the K vector spaces. Okay, but this is, I mean, this is a hard theorem. It's based on a hard theorem, and you have very little control on this omega. Okay, so there is some. And that's not what I want to do now. I want to move on. I want to be more explicit about this because I want to concentrate on this category here, which I underline. Okay, so you can just classify in this case. Okay, so this is the work of Yuri Manin in a beautiful paper which we wrote in Italian, and it says that for the formal and regular singular, you have an equivalence with representations of Z, of the group. So here you should see again this as a sort of Deligne theorem. What Deligne's theorem was saying is that if you work only with regular singularities, then the Tanaka group associated to that will be just the representations of the fundamental group. Okay, so of course here there is no fundamental group looking at you in the face, but everybody knows that the Laurent series should be thought of as the punctured disk, and of course the fundamental group of the punctured disk is just Z. So this is an important point. Okay, so now I move on to the main bulk of our research, and which is the study of differential equations when they have dependent parameters. Okay, and I start with the categories which will interest us. So I have my DVR, which is complete. So K is the residue field, big K is the function field, and I go on and define according to the characteristic of the residue field. I define either differential equations just like before, so just coherent sheaves here, these k-linear operators which are satisfy Leibniz rule and are integrable. If the characteristic of the residue field little k is positive, then I can do the same thing, but then I need to bring in all differential operators. So this dx here is the ring of differential operators, which shows in AGEA 4. Okay, so this is non-Noetherian, so it's a very big thing, but you can do it as well. And of course, I want the formal version of that also. Okay, in case the residue characteristic is 0, and then I define things in the same way. So instead of finite dimensional vector space, I have finite dimensional modules. Okay, so these are the differential equations available, which interest us. So you have the equations, but the production of groups is not so easy, because of course before you have linear algebraic groups, which are subgroups of GLN, and that could account for everything that you need. Okay, every group that you need in your Galois theory was already known. They are subgroups of GLN. And now over R, there are more groups. There are groups which are not subgroups of GLN. Okay, and so I will have two ways of considering group schemes over R. The first one is the cheap one and easy one, is that I start with something on the generic fiber and I take the Zariski closure. So this is a little theorem, a small theorem, saying that the Zariski closure is still a subgroup scheme of GLN R. Okay, so this is a standard technique of producing group schemes from the generic fiber. Or I can go with the Tanakian theory, okay, which I now explain. So again, you have this theorem which says that if you have an R linear abelian category, you have your tensor product, so it's bilinear, etc., etc., some other conditions, and I can throw in my category inside the R modules, and so T is a sub-abelian category of R modules, and it's stable on the tensor product, etc., etc. Plus one important condition, which was spotted by Serra, is that if you want your groups to be flat over R, you need this point here, which is that every representation or every object of your T should be the quotient of someone which has a dual. Okay, so if you think of a group, your object of representations will be R modules, right? So R modules, you have torsion R modules, you have non-flat R modules, and everything. So in order to have a decent theory, you will need this condition here, which is saying that every representation should be the quotient of someone which is free, which is locally free. So this is the condition. And if I throw in all these things, then I can say that my category T is equivalent to the category of representations of a flat group scheme, a fine group scheme. Okay, so this turns on the machinery and allow us to make some progress. Okay, so now I come to the differential Galois groups in these theories. So I give myself my scheme X, I give myself my point, and I give myself a differential equation which is R flat. Okay. So once I've done that, I just like before, I construct this category of objects generated by E. Okay, so subquotients, just like before, subquotients of tensor products, etc., etc. And I apply my construction, my two construction techniques of group schemes. The first one is the Tanaki, and the second one is the cheap one, which I just go to the generic fiber, then I'm over a field, then I can do Galois theory, the standard Galois theory, and I do this procedure of taking the closure inside the corresponding GLN. Okay, so I can construct two groups associated to that. And then you have a theorem which will be able to explain a little bit what these groups are. And the first thing is that the representations of this Tanakian one is a full subcategory of the differential equations, but I lose the linear algebraic property. So this Gao, this Tanakian Gao is not anymore a closed subgroup of the GLN. Okay, so I lost that. So usually it will be very big. On the other hand, the small group, it doesn't have this fullness property, so you lose that. But at least he is a closed and subgroup, so it's an algebraic subgroup of GLN of the fiber. And the two are generically isomorphic. So I have two different group schemes which are doing something in this theory. One of them is would be very big, the other one would be reasonably small, and the two have isomorphic generic fibers. So example, I take this differential equation, very simple one, okay, and this was, we learned this from Yves André, and so if you go if you compute the Galois group of the generic fiber, which means that you consider T as a variable in the field, right? You go to the Laurent series, then you compute it on the generic fiber and just out of spaces GM, okay, so it's one dimensional. So the generic fiber of the Gal prime is GM, but what happens is that you compute Gal prime and it turns out to be this funny guy here. Okay, so I call Gal prime a lasso, okay, because it looks like a lasso you use to take cattle, right? So what happens is that I get a group scheme which is a spec R here glued along GMK. Okay, so GMK is the GM over the fraction field, which I glue with spec R. So said differently, so this is this join here. Okay, and why is that? The reason is that this equation here, when I reduce modulo T to some power, it becomes trivial. Okay, so it means that reducing modulo T should be this part here of the picture, and reducing modulo T being trivial means that there is nothing of Galois at this point here. Okay. And well, and then you will say, well, this is a bizarre group, right? Because well, look at the picture. Okay, so you glue something over K with a copy of R. So this is a bizarre thing, and we can ask how common are they? And something which we did found out is that for projective spaces, okay. If you here, I'm not on a projective spaces, I'm on the affine line, but on projective space, this sort of thing doesn't happen because the Gal prime, it is a free R module, okay. So this guy here is not a free, does not give rise to a free R module. So these groups they do happen, but they do happen in these non-regular singular situations. Okay, so now how can I pass from gal to gal prime? And this is the theory of neuron blowups. Okay, and what is a neuron blowup? Neuron blowup is just considering one part of the usual blowup. Okay, so suppose I have a group scheme over R, and I have a closed subgroup of the special fiber, right, H naught. And then the neuron blowup is just the group scheme obtained by adjoining this T minus one of the ideal. So I divide every element which vanishes on H naught by T. Okay, so this guy here really is just one piece. So if the usual blowup, it's a projective thing, so it has many copies. And this neuron blowup is just no. I take one copy only. Okay, I just take one chart. Okay, so this was studied by Neron and Waterhouse and Weisweiler. And this is one neuron blow up. And then you have the one we studied, which is the formal blow up. And the formal blow up is that instead of giving yourself a closed subgroup of the special fiber, you give yourself a closed subgroup of the completion. Okay. So because of that, I have an ideal every time, an ideal corresponding to this closed subgroup of G. Okay, so H times H reduced modulo Tn plus 1 gives you a closed subgroup of that. And I, instead of taking just one neuron blow up, I take all of them. So I start adjoining, as I go on, I start adjoining more and more division by T. Okay, so some easy facts about these neuron blowups. The first one is that it doesn't change the generic fiber. This is pretty obvious because I'm constructing it by looking at the generic fiber. Okay, by adjoining elements of the generic fiber. And this is a different property of the blowup, where usually we are in algebraic geometry, we used to think of the blowup as dominating the whole variety. But it just so happens that with the neuron blowup, I'm looking only at one chart. So the neuron blowup on the special fiber, it falls inside of H naught. It falls inside of the scheme which you are blowing up. And it's universal for this property. It means that if I have another group scheme which has a special fiber sitting inside H naught, then it has to factor through the neuron blowup. And the very nice property is that the kernel is an abelian group scheme. Okay, so this is rather nice. And some facts about the formal blowup, which we studied. The first one is the most obvious one. It's usually not a finite type because you are joining a lot of stuff. It has the same generic fiber because you are joining just stuff which are rational. You're just dividing by T to get this guy out of this guy. And the most pleasing property is that their completion, right, is the same. Okay, so when you complete the neuron blowup, this formal neuron blowup, you obtain just the formal group you started with. So the example, and it's also universal in the same as before. So the example I can give you is the lasso, which I gave before. You take the closed point of the origin of the completion, and you apply this neuron blowup, this formal neuron blowup, and you get your lasso. Okay, and you get what you had before. So that bizarre group scheme which showed up is a particular instance of this construction. Another one which will show up a little later is that you can take the graph of the exponential function. So the exponential function in this situation is a formal subgroup of GA times GM complete, and it's not algebraic. Okay, so it's really a formal subgroup of that. And you take the completion, and the pleasing thing is that this guy here is a free R module. So the fact that this group is not algebraic gives you a very different flavor between these formal blowups and formal blowups of subgroups which are algebraic. Okay, so recall that the ring of the lasso, it was not a free ring, it was not a projective R module, but in case of the exponential, in which H is not an algebraic, it is a free R module. Okay, so the importance of blowups is let me tell you why is it that one has to study them. It's interesting to study them. The reason is that every blowup, every generic isomorphism between affine group schemes is a composition of Néron blowups. But the point, the annoying point is that it's a composition of infinitely many. So what happens is you take your first, you have a generic isomorphism. So you go to the special fibers. And on the special fibers, you have the image of G, curly G, inside of G on the special fiber. So this gives you a subgroup scheme, you blow up, and then you get a map. And then you do the same game, you blow up, you blow up, you blow up, and eventually you reach G. So this is an infinite thing, and it might be difficult to compute with that. And if the interesting point which we found out during our researches is that at least if characteristic K is 0, then generically isomorphisms to algebraic group schemes are formal blowups. Okay, so so it means that up to some level, so let me say like that because it's clearer, but it's imprecise, but it's clearer, says that any generic isomorphism, okay, with G of finite type will be a formal blowup of some closed formal subgroup scheme, okay? So this is the slogan. It's not true, but you have to adjust a little bit, but it's almost true. Okay, so now I want to calculate. So I reached the final part in which I want to calculate things. And so how is the Tanakian theory over a DVR going to be applied in case of an abstract group? So you have an abstract group and you have a representation. And you want to be able to detect what is the Galois-Tanaka group, okay? So as before, if you had a subgroup of GLN, which was in which the image of rho was dense, then this would be the Galois-Tanaka group, okay? In the present setting, it's not enough to have density because you have two fibers, okay? So, but the same principle applies. If I have a subgroup in the weak sense, it's a subfunctor of GLN R, okay, G, and if I know that the image on the generic fiber and on the special fiber is dense for the respective Zariski topologies, then the Galois-Tanaka group is G. Okay, so this is a way to detect whenever a group is the Galois-Tanaka group. So another way of saying this is that given rho, how do you compute the Galois-Tanaka group? You have to find a group scheme such that rho is dense on both fibers. Okay, it's dense. The image of rho is dense on both the fibers over K, over big K, over little k. But that's very unnatural. And the reason this is interesting is that you get already interesting outcomes. Okay, so that group which I mentioned before, it appears as a Néron blowup already of Z. Okay, but it appears as a Galois group of Z already. Okay, so this is pi of this row. Okay, so this is the Galois-Tanaka group here, and this is the H. Okay, the graph of this formal exponential, and this is this very silly representation. Okay, this is a very silly representation, and you already have these guys showing up. So they are very natural. So we are happy with that because we found a class of group schemes which really helps in giving names and describing the objects of the Tanaka theorem. And now we move on to the Leon's theorem over CT, okay, which is more or less the objective of this talk. And I work over C double bracket T, okay, and I take a smooth and proper over X. I take a divisor with relative normal crossings, so I'm going to think of P1 minus points, okay, if you wish. And well, you call it the punctured puncture X by X star. Again, you consider the logarithmic differential forms, just as before. So you throw in the poles. And you define regular singularities just as before. So first you define logarithmic ones, and once you define logarithmic ones, you look at their image in the differential equations over X star, which are image of logarithmic things. So now, if I give myself a differential equation, I will say that it is a regular singular if it lies in the image of logarithmic, which means that it has a logarithmic model, and if and then I will have a Deline's theorem again. Okay, but this one we proved. So given a differential equation over X star, I can truncate modulo Rn. So this is a finite, Rtn is a finite dimensional C algebra. So I get a complex space Xn, because this is finite dimensional. So I get a complex space, and I get a differential equation over this complex space. And this gives me a representation of pi1 of the topological fundamental group of this space. Okay, but the topological fundamental group of Xn star is just the topological fundamental group of X0, because this is an infinitesimal deformation. So you get a representation of pi1 on R modules passing to the limit. And this is what I call the monodrome. Okay, so you stack them up and you get the monodrome. And the theorem that we proved is that the differential equations over this X star, which are regular singular, so this is Schlesinger's theorem or Deline's theorem, whichever one, is just equivalent to the representations of this this X0 star. Okay. And in the formal setting, we were also able to obtain a similar result as the previous one, as in Manin's theorem, but it's a classification one. It says that the formal over R, so here you consider Rxx modules, is equivalent to the category of representations of Z. Okay, so this is not written down yet, but yeah, it's almost finished. And okay, so now for the examples, you can say, well, this is the good thing about these theorems, that they give you very simple ways of computing things and finding non-trivial results. And if I give you this differential equation, right, this simple differential equation over GM, I can use the theorem to say that this is regular singular, so I only need to take care of the representation of pi1, and the representation of pi1 in this setting was the representation which I mentioned here. So you do the calculation, it's just this representation. That's why I introduced it here. And once you do that, let me go back. Once you do that, you see that the Galois group is the Tanaka Galois group is the same as the Tanaka Galois group of the representation, which is this interesting fellow here. Okay. And let me end with an idea of proof of this theorem. Okay. So I'll give you the idea of proof of the formal theorem, because the other one is just a more analytic stuff and takes more speech to describe it, but the idea is exactly the same. So the idea is to, in every linear category, I consider the category of Rn modules in there. Okay. So these are objects of the category C with an action of Rn. So then I apply Munin's theorem, and I say, recall that the regular singular formal was equivalent to representations of Z. So the Rn modules in here are the same as the Rn modules in here. Fine. But then if I take limits of Rn modules, so what is a representation of Z with an action of Rn. And this is compatible, so if you go on the limit, so you just get a representation of Z over R. Okay, so you can take the limit. But the real point is that here you cannot take the limit on the differential equations part. Why? Because R double bracket T is not t-adically complete. So if you take a limit of Rn x modules, it will not give you forcefully an R double bracket x module. So let me show you just what can go wrong. So this is the simple differential equation, okay? And what goes wrong is that you consider these guys which have larger and larger poles, but they depend on Tn. And what happens is that this differential equation here, when you reduce it modulo n, it becomes trivial, okay? Because this here is the trivial differential equation. This here is E reduced modulo T to the n. And because of this guy here, because of this this element F, this is horizontal. So these are, this is killed by the derivation. Okay. So at the end, what happens is that if you don't have regular singularities, what happens is that you can get poles every time you change T, your poles get bigger, which is like so here. Okay, if I truncate T, it's over, right? But if not, this is done. So I guess I'll leave it here, and I give you some text which used in this talk. So thank you very much for your attention, and I'll happily listen to the questions if there are any.
Yeah, thank you, João Pedro. Now we have time for questions, if any.
Right. I just have a curious question. So if you assume the Galois group is somehow nice, for example, it's a reductive or semi-simple, does that say anything about this differential equation?
Sure, you will. Yeah, the best theorem you get is, for example, the one I mentioned. If you assume that the Galois group, for example, is solvable, then you can obtain your differential equations by solutions of integrations, exponentiations, and so on and so forth, right? But in the case of general GLN, etc., no, you wouldn't be able to say much about the differential equation.
I think the question is usually the inverse one, the converse one. So you just look for some system that have the Galois equation, Galois group equal to GLN or some other semi-simple group. This is kind of inverse Galois theory, right? But not specific characterization of such a system.
Yeah, but the other way around is, for example, this is a beautiful theorem about the solvable case. If the Galois group is solvable or unipotent, then you can solve it by exponentiation and integration, which is.
But for semi-simple, I think.
Yeah, for semi-simple, you get a little stuck. Yeah.
Yeah.
So.
Okay, so I suppose there are no other questions. So let's thanks João Pedro again, and thank you all for attending the